Here we go. All right, so I'm gonna do a little experiment for you. Are you ready? Here's what I want to know. If I take a propane torch, and I use it to heat a piece of iron, how hot will the iron get in the torch here? You're going to figure out how hot it's going to get, okay? Now to do this, we're going to do a couple things. Could you come on up here, Ben? And I've got a cup of water. I would like Ben to go weigh the cup of water back there. In the scale, the orange thing back there. Go weigh the water. Here's what we're going to do. When this thing gets nice and hot and it's glowing red, I'm going to drop it in the water. So we're just getting this sucker hot. You got it back there?
235?
What?
235.
235, that's grams. Okay, good job. Thank you. So, we're going to do a calculation. So we need to know how much water we have. We have about 235 grams of water. And we need to know its temperature. So, Naomi will take the temperature from you. Come read us the temperature here while I'm warming this up. It's getting hotter. What do you think? What's the temperature of that?
21.
21? Is that like with two significant figures? Could be 22, might be 20? Or is it 21.0?
21.
All right, so it's 21.0. Meaning it could be 21.1, it might be 20.9.
Yeah.
All right. So that's the initial temperature of the water. Get the thermometer out so we don't break it. So we're starting to get hot here, right? Can you see that? The tip of the blue flame is the hottest part. So what's going to happen is this piece of iron has lots of thermal energy. Its molecules are moving really, really fast. In fact, they are moving so fast that if you touched it with your finger, the molecules on your finger would move so fast, the water would all leave, and the ones that would be left would move so fast they'd collide into each other and they'd rip the cells apart, and it would kill the skin. Okay? So, they're moving pretty darn fast. I'm not sure it's going to get too much harder here. Starting to get a little glow. All right, so here goes. I'm going to drop that in there as fast as I can. Okay, so the metal was hot. It had thermal energy. I dropped it into the water, and now the metal's not so hot. In fact, I can hold it. Where did the thermal energy go? It went into the water. We transferred thermal energy from the metal to the water. Okay? So what we're going to do is we're going to see how hot the water got. So if we stir it for a minute here. All right, Garrett, come on up here and help us. Garrett's going to give us a temperature reading. What do you think?
30.1 or
30.1. Is it going up still?
Yeah, it's probably about 31 and a half now.
Oh, we better wait another minute then. We want to wait until it stops going up. You're going to trip me there, Naomi.
Can I unplug one
No. Is your computer dead? You don't need it right now anyway.
It stopped at
30.2 or 32?
32.
32 is the temperature. Stop going up. So all the heat is transferred. Okay? All right. So we're going to see if we can figure out how hot that piece of metal was. Okay? So we got two things. we have a piece of iron and we have water. Which one gained energy? The water gained energy. So if I made a little diagram of what's going on, this is the change in temperature, this is Q. The water gained energy. We added heat to it and the temperature went up. What happened to the iron? It lost. So it lost energy and its temperature went down. Okay? Now let's fill in a couple of details. The water. What was the mass of our water there?
235.
Yeah. So about 0.235 kilograms. The temperature of our water initially was 20.9. All right, 20.9 degrees Celsius. And the final temperature of our water was what? 32.0 degrees Celsius. Now, do we know the heat capacity of water? You guys know it already? Oh my gosh, you're turning into geeks. 4,186 joules per kilogram degree Celsius. So can we find out how much heat the water gained? Maggie, what equation will we use to find out how much heat the water gained?
Q equals N times C times delta T.
Okay. All right. So grab your calculators and let's calculate how much heat the water gained. You know the mass of the water, you know the heat capacity of water, and you know the change in temperature of the water. So how much heat, thermal energy, did the water gain? Mind your way here. So we're calculating how much heat the water gained. I'm still on the video, that's good. And Jeff, you get an answer? Not yet. Anybody? Reagan, did you get an answer? 0.235 times 4,186 times, and then, so we're going to take the mass times the heat capacity, and then take the final temperature minus the temperature of the water initial. That's delta T, right? So that's going to be 32 minus 20.9. Plug that all in. Help me here. Gabby, you got it? Good grief. You got it, Camden? What'd you get?
31,457.82.
Whoa. Little up. Anybody else get that?
No. 10,919.
That's all I got.
Yeah.
10,900? Something went wrong there. 10,900 joules. That's about right. Run your calculation if you didn't get that, guys. Try it again. Make sure you get it. All right. Now, did the water gain energy or lose energy? It gained it. So this is positive, right? Remember our convention? If something gains energy, Q is positive. If it loses energy, Q is negative. All right. So where did that energy come from? The iron. So the iron must have lost how much energy?
10,900.
Yeah. That's called the conservation of energy. The energy from the iron went into the water. So that means that for the iron, we know Q must also be 10,900 joules, except the iron lost it, so that would be negative. Right? Now, do we know the mass of the iron? Do we know the mass of the iron? Not yet. So we're going to find the mass of the iron. So, let's grab it. All right. Who has it? Damon, here you go. Find the mass of the iron there. Make sure you zero the scale before you read it. So Damon's going to find the mass of the iron for us. Push the big T button on the right to tear it. Should read 0 now. So the mass of the iron, and I'm going to use a little I for iron so I keep it apart from the mass of the water, is
39.5.
0.03 what? 395. And that's kilograms. I did a conversion. You said 39, right?
Yes.
Okay.
Right over Garrett's head.
Whoa. I wasn't so how much. Gotta work on your projectiles. All right. We also know the heat capacity of iron. Anybody know that? Oh, darn. I would have been really depressed. 448 joules per kilogram degree Celsius. So can you guys tell me how much the temperature of the iron changed? Now we got one itty bitty problem. That's negative, right? So the change in temperature is going to be negative also. All right? So take Q equals MC delta T and find delta T. How much did the temperature of the iron change? Okay? So take Q divided by M times C, and you get delta T. So what is the change in the temperature of the iron? So take your negative 10,900 divided by, and please make sure you group your denominator here. Sorry. Group your denominator there. What do you get, Natalie? Negative 600 and, let's go with negative 616. That's degrees Celsius, right? So here's the question. If the iron ended up at 32 degrees, because the iron and the water were mixed, right? If it ended up at 32 and its temperature changed by negative 616, what was the initial temperature of the iron? So what we're going to do is we're going to say that the change in the temperature of the iron is the final minus the temperature of the iron initially. And if we want to find this, what do? We take it to the other side, right? So temperature of the iron initial will equal the temperature final minus delta T. So that's going to be, I'm not even sure the video can see this anymore. The final temperature was 32 degrees Celsius minus a negative 616 degrees Celsius. So that is a 648 degrees Celsius. That's how hot the iron was. We can figure it out using conservation of energy. That process is called calorimetry, the science of studying energy. Okay? By the way, 648, how do we find that in Fahrenheit? Multiply by 1.8, and then add 32. So what's the temperature in Fahrenheit of the metal in the burner? A little over 1,000 degrees. Okay, there you go. Does that sort of make sense? So here's what we're going to do. We're going to use the conservation of energy idea to solve problems when heat is exchanged. Okay? Now we're going to do it a little more formally than this. We're not going to work through all the parts. We're just going to do it all at once. So here's the big idea. The big idea is that the energy that is lost, does the energy that's lost equal the energy that's gained? It does. Negative 10,900 equals positive 10,900? You can't quite say they're equal, but you can say the sum of the energy transfers add up to 0. Okay? So if your dad gives you 20 bucks because you can't go anywhere, it's COVID. But just in the old days, your dad gave you 20 bucks and you went to Frosty Boy. Okay? What was the net change in your dad's worth? Minus 20. What was the net change in your worth? Plus 20. Would you say that those are equal? No, you would say the sum of all transactions in the family add up to 0. The negative 20 from your dad and the positive 20 from you, the net worth of your family didn't change, right? So here's where we end up, and this is how we write it. A lot of people get confused and they say Q lost equals Q gained. And then they get negative signs they don't like, so they just erase them. That's how you work in chemistry, right? Ah, there's a negative there, I'll just erase it, pretend it's not there. Here's how we deal with the negative signs. Here's our big idea. The energy that is gained plus the energy that is lost must add up to 0. So plus 10,900 plus a negative 10,900 must add up to 0. That's the statement of conservation of energy. Okay? And that's the only new thing today. Right there, there's your notes. So when 2 or more systems or 2 or more substances exchange energy, the total sum of all energy transfers adds up to 0. Okay? And now I'm going to put that together and solve an example problem of how this all works. So, give me a second to switch gears here. Now, you're going to solve the example problem with me because it's your first homework problem. Okay? So we're going to do the first homework problem together. And then you'll put it in and you'll all have it right. Let's see, here we go. So when I did this earlier, I actually did it on a Bunsen burner. What's that? I did it on a Bunsen burner and I got slightly different numbers. So I'm going to go with the one I set up here. Here it is. I have an iron slug and it's actually 0.03, so 30 grams, not 40 grams. This one was a little heavier. It's placed in an insulating cup of water. For this problem, we'll assume that the heat that is gained by the cup is negligible. So we're assuming that all the heat goes into the water. The cup doesn't absorb much heat. Do you know why? Not much heat goes into the cup. What do you know about cups? Styrofoam cups. Do you care if somebody throws a styrofoam cup at your head? Why not? Because it has almost no mass. If something has no mass, or a very small mass, it can't hold much heat, right? So styrofoam don't have very much mass. They don't hold very much heat. So we can ignore the heat that goes into the cup. Okay? That's that part. The 240 grams of water is initially at 24, and the final temperature is 36, and I want to know what is the initial temperature of the iron. So this is just like we saw in our little demo, right? But I want to show you how we're going to put it together as a solution. So the first thing we're going to do is what? What do you think? Draw a diagram. That's right. I'm not sure how far I can go here. Let me take a look. Ooh, I can go about here. All right, so our diagrams are going to look like this. We are always going to draw a diagram, and we are going to show Q and delta T. Okay? You can draw teapots, and you can draw beakers and everything you want, but you haven't got the diagram until you draw the graph. Okay? Now, what happens? Well, some water warms up, and some iron cools down. So let's put those on the diagram. Some water is going to warm up like this, and some iron is going to cool down like that. And they're going to meet at the final temperature. And I want you to label your diagram so I know what's going on. This is the water that is warming up, and this is the iron that is cooling down. Okay? And to keep things separate, I'm just going to use M and I as my subscripts, okay? All right, now, the variable list. It looks intimidating, but don't be too frightened. I lost my black marker. Here it is. The variables we're going to have are as follows. We're going to have the mass of the water and the mass of the iron. We are going to need the heat capacity of water and the heat capacity of iron. We are going to need the temperature of the water initial and the temperature of the iron initial. And we would need the temperature of the water final and the temperature of the iron final, except the final temperature of the mixture. They're both the same final temperature. So do we need to keep different variables for the final temperatures? We don't. So I'm just going to have T final. Okay? If the two things end up at different temperatures, then you would have to have two different T finals. But fortunately for us, we're always going to wait until the two temperatures come to be the same. Okay? All right, so now we got to fill in our list from our problem. So what is the mass of the water here? 240 grams or 0.240 kilograms. The mass of the iron is 0.030 kilograms. The heat capacity of water is 4,186 joules per kilogram degree Celsius. Iron is 448 joules per kilogram degree Celsius. The temperature of the water initially was 24 degrees Celsius, and the temperature of the iron initial is unknown. That's what we're trying to find, right? How hot was the iron? And lastly, the final temperature of the two in this example problem is 36 degrees Celsius. Okay? Everybody good so far? Can you confirm I have the right heat capacity for iron? Okay. All right. So there's my variable list. Now, here's how we solve the problem. Okay? We start by stating what idea we're going to use, which is that the energy is conserved. Okay? So we are going to apply this principle that the Q gained plus the Q lost must add up to 0. Okay? You've got to start there. Now, a lot of you want to do things like tell me, I'm going to solve for temperature of the iron initial. Can you really say that? There is no TI in this equation, right? This isn't even really an equation, it's a principle. So before you can tell me your plan, you've got to apply the principle, okay? So, what gains heat? The water. How much heat does it gain? It's the mass of the water, heat capacity of water, times T final minus temperature of the water initial. That's the heat that's gained, MC delta T. And since the water gains heat, that's for water. Now what loses energy? The iron. So plus, I'm going to have the heat that's lost is the mass of the iron, heat capacity of iron, times T final minus the temperature of the iron initial. That's delta T, right? Delta T is always final minus initial. So it's that mess that must add up to 0. And now you can state your plan. Now you can say, I'm going to solve this mess for the temperature of the iron initial. Okay, and we're going to try to do it algebraically, which means don't plug in any of these numbers yet. Let's get TI by itself. What would you do first? If I was trying to find the temperature initial, trying to find this thing right here, how would I get that by itself? David, what would you do first?
You subtract that whole right side.
Mass of iron, or you can do that too.
Well, this is, I want this, right? So I'm going to bring this to the other side by subtracting it. Okay? I think that's what you're saying, right? So we are going to be left with the mass of the iron, heat capacity of iron, times temperature final minus temperature of the iron initial, equals minus mass of the water, heat capacity of the water, times temperature final minus temperature of the water initial. What'd you do next, David? We're trying to get this thing right here.
Divide the mass of the iron and the
Yeah, this is inside of parentheses, so the whole thing is multiplied by m times c. So let's divide both sides by the mass of the iron, heat capacity of the iron. Mass of the iron, heat capacity of the iron. That cancels those. Now, do you need the parentheses anymore? Are they grouping anything? They're not, so we don't need them, okay? So what I really have is T final minus temperature initial of the iron equals minus the mass of the water, heat capacity of water, temperature final minus temperature of the water initial, all over the mass of the iron, heat capacity of the iron. And I'm trying to get this by itself, right? If I want the temperature initial of the iron by itself, I've got to subtract T final from both sides. So if I subtract T final from this side, it goes away, right? And I'm almost there. I want T initial. I have negative T initial. What do I do? You would divide by -1? Oh, I would multiply by -1. It doesn't matter. Multiply everything by -1, and you get the temperature initial of the iron equals, now this is going to be positive, mass of the water, heat capacity of water, temperature final minus temperature of the water initial, all divided by the mass of the iron, heat capacity of the iron, plus temperature final. And that is our algebraic solution. Woohoo! Grab your calculators. Plug in the numbers. Get your answer. Put it in your computer for homework problem number 1 and see if you're right. Okay? And if you are, move on to problem number 2. If you're not, keep trying and I'll help you. All right? That's the end of the lesson. So we'll spend the rest of the time solving the problems in problem set 3, which is just applying the conservation of energy. Make sure you start with this idea, apply it, tell me your plan, solve it algebraically. And make sure your diagram has labels and shows me what's gaining and losing energy. Okay? Does that make sense? All right.